All right, good morning, everyone. Thank you so much for joining today's webinar. Today, we're going to be talking about Markforged continuous fiber reinforcement. Just a heads up, this session will hopefully be about 45 minutes of content and then 15 minutes of Q&A. Unfortunately, there is kind of a lot of intricacies that go into fiber reinforcement. And worst case scenario, I probably won't get to everyone's questions, and that's okay. We will have a list of questions at the end, and then I will make sure to answer those questions and send a follow-up email so that you guys get all of your questions answered. All right, so my name is Kat Pomorski, and I am a customer success engineer here at Markforged, specifically for the East Territories. So I went to Penn State, and I was a materials engineer at Penn State, and I've worked for Markforged for about 4 years now. And so I've given this webinar a few times at this point, so hopefully I know what I'm talking about. I do. Anyway, so what really excites me is AM materials and design for additive manufacturing. That's why I love talking about fiber reinforcement, is because you can take a part that's not working for its application, if you've printed it just in plastic, add probably just a little bit of fiber to make it strong enough to be usable for your applications. All right, first up, what is continuous fiber reinforcement? Continuous fiber reinforcement is going to be the fiberglass, the carbon fiber, the high strength, high temp fiberglass, and the Kevlar materials. Continuous fiber reinforcement is basically just those continuous strands of the fiber that we add to our part to make our parts a true composite material, right? If we think about what a composite material is you add the properties of both materials to get the benefits from both, right? So we add the benefits from a plastic-based material to the benefits of our continuous fiber, right? So we think about the benefits of our Onyx plastic material. The benefits of plastic is it's non-marring. It's not going to scratch anything. It's typically a lot cheaper to use. It has that deformation. You can actually use the plastic deformation to grip things easier. Whereas that continuous fiber reinforcement is going to add the strength, the durability, the toughness that you're going to need for some of your applications. So I want to start off today's class looking at the different types of continuous fiber here, right? So we're going to look at the different types of continuous fiber. Then we're going to jump into how we place that fiber theoretically. And then we're going to talk about how to place it in Eiger. So again, 4 types of different fibers that we have currently, and let's talk about each one of them. First off, we have carbon fiber. Carbon fiber is going to be your strongest fiber. It's going to have the best strength to weight ratio. It's going to be very strong. And in this little GIF here that you can see in the bottom right-hand corner, we have our carbon fiber reinforced Onyx part compared to aluminum 6061, right? And aluminum can be a lot more ductile than carbon fiber can be. So if you want an incredibly strong part, you can use carbon fiber. Fiberglass is also incredibly useful, right? The problem with carbon fiber is that it's incredibly expensive to use, right? And in Eiger, I can show you how to optimize that fiber, but fiberglass is still going to be cheaper. Fiberglass still increases the overall strength of your part just a little bit more, right? It's definitely stronger than Onyx alone and ABS or PLA or any other plastic you're using, but it's still not as strong with fiber reinforced Onyx, in this case, fiberglass. So again, it's sturdy. It's going to be your most cost effective. In a lot of cases, you probably can use fiberglass if you just need a little additional strength from over a plastic part. Kevlar. Kevlar is incredibly impact resistant. right? So if you want to take something and toss it out of an airplane, if you wanted it to survive, you can use Kevlar. We've actually had customers drop it from really, really large heights to see if it will damage something. So Kevlar is really, really impact resistant. So if you're dropping something off of large heights, Kevlar is great. Another great thing about Kevlar is that it is incredibly wear resistant, right? So if you have some sort of rubbing motion between a part and say your Onyx printed part, you can add Kevlar. And once your part rubs through the Onyx outer shell, that Kevlar will be incredibly wear resistant. Also, the cool thing about Kevlar is it's yellow, right? So if something gets worn through your Onyx part and you're looking at, hey, when should I replace this? Kevlar might be a great option. Once you see that yellow, you can be like, hey, I need to replace this component. And then finally, we have high strength, high temp glass. So high strength, high temp glass is allowing you to increase the heat deflection temperature of your parts. And so when we look at high strength, high temp glass here, and in this little GIF, you can see that we have kind of the same setup where we have our high strength, high temp glass, reinforced Onyx, PLA, and ABS. What they actually did was they heated this up to 150 degrees C and then hung a weight from it. And again, you can see that that HSHT was able to better withstand that force. So you can increase the heat deflection temperature. Also, if you are increasing the temperature of a part, any sort of fiber will help keep everything together as you raise that temperature. So regardless, it'll help increase the strength to a higher level when you do increase the temperature. All right, so those are the 4 different types of fiber. We also have some variations of the carbon fiber for different materials. I don't want to go too much into that here. So one thing I want you guys to think about is something called toss. It's your type of fiber, your orientation on the print bed, your strategy for adding fibers, and your settings on your individual layer, right? The biggest one is your type of fiber, which we just talked about. We will talk about these 3 other, the OS and TOS, right? We will talk about those other 3 here in the rest of this segment, right? So we're gonna take a step back, right? We're gonna take the knowledge that we just learned in the past like 10 minutes about what fibers do what. We're gonna forget that for a second. And we're going to talk about the very basics, right? So if you took any mechanical engineering classes, this might be familiar. And it also might have been a couple of years since you've done this. So just a refresher for everyone. First things first is that continuous fiber is strong in tension. So if you are adding fiber to a part and you ask yourself, hey, is this addition of fiber helping this part be stronger? If that fiber is in tension, it will be stronger, right? The biggest key when you're doing anything with continuous fiber, or if you're doing really any design for additive manufacturing at all, is you have to think about where the forces are coming from, where the forces are being applied to your part. From there, you can decide the orientation on the print bed. And then once you do that, then you can add fiber. But as long as that continuous fiber is in tension, it will be increasing the strength of your part. Cool. So there's a video out there that's really cool. It's this chain link that we pull in tension, right? And that chain link was able to withstand, I think it was like 22,000 pounds of force before it broke, right? And that is just how strong continuous fiber can be in tension. Now, that's a perfect scenario. Usually you don't have that perfect of loading conditions, but it just goes to show you how strong it is. That's something that we will also send out in our follow-up if you haven't seen it yet. It's really cool to see. So the real basics that I want to talk about is beam bending theory, right? This is the mechanical stuff that you may have learned back in college. Beam bending theory basically says that if you apply a force to the end of your beam on one end, and the other end of the beam is affixed to the wall, and when I apply that force, that beam is going to bend, right? Makes sense. If I apply a force to a beam, it's going to bend. Okay, bear with me here. So if we look at a cross section of that beam, this is kind of just like that middle section right there, you're going to have a neutral axis where the equivalent force is basically 0. You have tension force or tensile force on the very top of the beam, and you have a compressive force at the very bottom of the beam. And then you can see that there is some amount of force present going towards the neutral axis, although it's much less, and then it kind of flips over, right? So the very high tensile force on the top, very high compressive force on the bottom, and some amount of forces between the two. Okay, why do we care about that? Well, we want to know where the extremes of those forces are, because we want to add fiber where it's going to be the biggest impact, right? Again, carbon fiber and really any of the fibers can be very expensive. And so we want to understand where the extremes of those forces are so that we can put fiber in those locations. It's going to give us the biggest benefit, right? So we're going to add carbon fiber on the very top of this beam and the very bottom of this beam to make sure that we are counteracting the highest forces, right? Now, just take a second and think about what construction material that we use in everyday life that uses pretty much the same principle. And the answer to that is those I-beams, right? We use I-beams for construction materials. I-beams have a ton of material at the top, a ton of material at the bottom, and then you have a thin section in the middle, right? Because we're putting that material where we see the highest forces, right? And so you can kind of think of carbon fiber, or any fibers, the exact same way. We typically like using fiber in a sandwich panel, right? And the sandwich panel idea is not new. It is very similar to traditional composite materials or traditional carbon fiber layups, right? You still have, or you typically use a sandwich panel. So we're taking the idea from traditional composite materials and using them in our 3D printing idea as well. So we want to use our fiber in a sandwich panel. What the sandwich panel does is it allows you to, increase the stiffness of your part, right? Very, very, again, similar to that I-beam, where the top and the bottom are going to be typically, right? It's easy in a square, but this is going to be different for your parts. The top and the bottom of your part are going to see the extremes of those forces. But with the sandwich panel, it also allows you to increase the stiffness of the overall part. So sandwich panels really add to the bulk stiffness of your part overall, right? And this is kind of the whole, again, there's science and math behind it. I don't want to get too deep into that. This is kind of showing you what it is in the beam deflection theory, right? This is what it looks like. This is why we use sandwich panels, because if those sandwich panels are farther away, so they're 4H as opposed to just H, you're going to increase the stiffness of your part exponentially. So just by adding sandwich panels, you can get an incredibly strong part, right? And there's a good example of this. And again, I can't talk too much about this, but if you take a look at, we always have these sample keychains that we send out. One's just onyx and one's carbon fiber. You can still bend the carbon fiber one a little bit, you can still see a little deflection because it's incredibly thin. Now, if I made that 5 times thicker, there's no way you'd be able to bend it, right? It'd be much stiffer the larger thickness that I add between those sandwich panels. So when I get asked the question, where should I add fiber? There's 2 spots, right? There is the sandwich panels, and that's going to be at the very top of your part and the very bottom of your part. And then also where you see the extremes of your geometry change or where you see the extremes of your forces. So that's the biggest key, right? Very top, very bottom of your part, and where you're going to see the extremes of your forces. That is how you most effectively path your fiber, right? If you notice in Eiger, and we'll hop into Eiger here in a minute, when you turn on continuous fiber, it'll automatically put fiber at the very top of your part and the very bottom of your part. And this whole theory is why. And again, we're really just stealing this from traditional composite manufacturing. One thing to keep in mind is that continuous fiber really only reinforces on the X and Y plane, right? It is still a 3D printed part. So you're only going to see significant reinforcement on the X and Y plane, right? And there's some caveats to this, and there's ways to get around this, but that's not what this webinar is about. We're going to make this webinar series reoccurring. So we talk about all of this stuff that's maybe common knowledge to us internally at Markforged, but we want to be able to share with everyone else. Okay, so we're going to go ahead and apply it, right? So this is a tube bending die. And this is one of my favorite examples, and I'll use it quite often because I think it shows design for additive manufacturing very well, but also we can talk about forces applied here, right? So if you're not familiar with tube bending, that's totally fine. Basically what you do is you have a die like we see here. We take a tube, we have another die that clamps onto it, and it kind of twists together in order to form the correct shape for the tube, right? First things first, when we're trying to decide where the continuous fiber is placed, we need to know, again, where the forces are coming from. In this case, we have a ton of forces from the tube onto the part itself, right? We also have some forces on a machine key, but we don't have to worry too much about that right now. And this is just another cross section here, right? Again, the tube is really putting a lot of force into every direction. And then here's a picture of that machine key as well. That's also applying some sort of torque load onto the part. So it's something to be aware of. Oh, here it is. There we go. better image, right? So we're going to take the knowledge of our forces from that tube bending die, and I'm going to show you how I would go and path it in Eiger. And if you do it differently, that's totally fine, right? Before we do that though, I want to quickly talk about the different types of fiber reinforcement, right? So we have a couple different strategies. Again, sandwich panel. Always should have a sandwich panel, right? The very top and the very bottom of your part, because that is going to allow you to have the maximum amount of stiffness. Another thing that I didn't mention, but it's good to mention here since it's on the slide, is that it allows for a good balance, right? Because carbon fiber, or any of the fibers really, they don't shrink and change like the plastic does. And so if I have continuous fiber on the very top of my part only, I can actually see a little bit of warping in my part because the shrinkage of the top is much lower than the shrinkage at the bottom of my part. So if you get warping and you have a very dense section of fiber in one area, that might be why you might need to evenly space it out more. Next up, we have fiber striping. Fiber striping allows you to say, hey, in this portion of my part, I'm going to add 17 fiber stripes. So I'm going to have 17 stripes of 4 layers each. And again, this will make more sense once I actually show you an Eiger. And then finally, you have shelling. Shelling basically just will apply fiber to the entire outside of your part, and it'll help all of your walls be reinforced, and it will help your part be a lot stronger in compression. So that's something that we may want to do with that 2 bending die. We'll actually apply all 3 of these with that 2 bending die. And then finally, we have concentric versus isotropic fiber, right? Concentric fiber is basically just creating outlines of the shapes of your part, right? So if you have, let's see here, we'll just say like my phone here, right? If I want to use concentric fiber, it'll follow all of the corners to create the concentric fill, right? Isotropic is going to be more of a basket weave pattern. And so basket weave pattern usually comes in layers of 4, right? So it's what, 0, 45, 90, 135. That allows you to add continuous fiber in pretty much every single direction, right? And so concentric fiber is really good at helping with bending along the z-axis. And the isotropic fiber is much better at helping with bending along the x and y axis. Okay, so now we are going to jump over to Eiger here. And just a heads up, if you're not super familiar with Eiger, that is okay. One of my colleagues, Michelle, will be starting an Eiger class, and I'll have that at the end of my class I'll talk about here. Okay, so this is that 2 bending die. This is the way I oriented this part. You can see that we added bolts here as well. Bolts allow you to compress the part so that it helps prevent any of that z-axis weakness. Again, don't want to get too much into that in this class, or this webinar, I should say, but I did want to mention that. We're going to worry just about how I'd fiber path that. So again, just to remember where these forces are coming from, we have the tube that is applying a load to this curved section, right? We also have the machine key applying some torque similar to like that, right? So as we kind of have learned throughout the rest of the section, is we are going to add fiber at the very top of this, and the very bottom of this, right? That's going to be our sandwich panel. It's going to increase our max stiffness. And then we're going to look at adding fiber in the extremes of our forces. In that case, a lot of our forces are going to be centered around this curved section. So we probably want to add fiber there as well. Okay. There's one other place that I would add fiber, but we'll get to that here once I jump in. All right, first things first, right? We want to add our reinforcement material. I'm going to go with carbon fiber. Doesn't really matter which fiber you use. The one thing that does matter with fibers is you have to remember that carbon fiber has a set layer height of 125 microns, whereas the other fibers have a set layer height of 100 microns, right? And so if I was going from carbon fiber to fiberglass, that changes the amount of layers in my part, and therefore will change my pathing. So I'd have to redo all my pathing if I designed it for carbon fiber and then changed it to fiberglass. So you just want to be a little careful about what fibers you end up using. Okay. So the only thing that you're going to do in this main screen here is choose your reinforcement material. Everything else needs to be done in the internal view. All right, so you'll notice what I mentioned before. we have continuous fiber at the very top of my part and the very bottom of my part, because we told Eiger that's going to be where we want to add those sandwich panels. The only problem with that is that Eiger right now is not smart enough to know that the top of my part really isn't giving me a lot of fiber, right? I want the top of my part to be the large flat section that matches the bottom, right? We want this to be very even so we don't have to worry about warping, right? This part wouldn't warp realistically, but just for the sake of it, we want to have that good practice. So we can go ahead and just delete that top layer of fiber because we are going to place it ourselves. I like to start out, and this is how I add fiber. You can do it totally differently if you want. This is just what I like to do to be very, very precise about it, right? And this will give you the most optimal amount of fiber. So what I'm going to do is I'm going to go towards the top where I want to add fiber. And an onyx part is comprised of 4 roofs, 4 floors, and 2 wall layers. So what I'm going to do is I'm going to find where I find the first roof layer. It's here at the very top. I count down from 4 because I always typically want to have 4 roof layers. So 1, 2, 3, 4. And then on the 5th layer is my first layer of infill. And this is the layer where I'm going to start adding fiber. So I'm going to go and create a new override, and I'm going to add fiber. And then just give that a second. Okay. Now what I can do is I can head to my 3D view, and I can use that first layer of fiber that I selected as a starting point, right? So that's my starting point. And then I've selected 3 additional layers, so 4 layers total. Again, 4 layers gives you nice uniform strength across the part. And I'm just, again, going to create a new override, and I'm going to add fiber. Give that a second. And again, if we look at that 2D view, now we're able to see we have 4 layers. So 1, 2, 3, 4. Oh, I didn't quite get 4, but that's okay. I can always move it if I need to. Awesome. And then you just keep doing that for the rest of your part, right? So we got the very top of the part and the very bottom of the part, right? That's going to give us our max stiffness. Our second location is the extremes of those forces. So the extremes of the forces are going to be in that curved section because that is going to be where the main force is applied. Again, I'm going to do something similar here. I'm going to find where I want the start and the end point of my fiber in the 2D view, and then create an entire section in the 3D view. This is, again, just how I like to do it because I think it's pretty quick to do it this way. But what we want to do, it's kind of hard, it might be hard to see here. I'll try and zoom in. Is again, you can see that we start to have these roof layers on the outside where we start to get that tapered shape. So we want to start in the area where right above that roof layer, or sorry, right below that roof layer. Again, I'm going to add fiber. That's going to be my starting point for that curved section. I'm looking at exactly where that curved section is going to be. I'm going to do the same thing on my top section of that curve. There you go. This layer no longer has any roof layers on it, right? And you can tell the roof layers because they're these little squigglies here, right? They're solid. They're not like this infill section here. And again, I'm going to go and add fiber. And again, this is going to be really my end point. So I can see that from layer, oh, what is that? From this layer, So this layer is going to be where we add that continuous fiber. And again, we're going to add the bulk of the continuous fiber in our 3D view. So again, I'm going to pop back to that 3D view, hold and drag to get the section from my one fiber starting point to the other. And then again, I'm going to create a new override and I'm going to add fiber. Now again, when I'm adding fiber, I have to ask myself, is this fiber in tension? If the fiber is in tension, it's going to be useful. In this case, right, we probably do not need isotropic fiber because it's not really adding a lot for us. We don't really need to rotate because the forces are all in kind of one area. So what we can use instead is we can use concentric fiber, right? Concentric fiber will just outline that curved section. And that's really where the forces are being applied. And again, you'll have to give this a minute. It's going to take a minute to pass. But I'm going to use concentric fiber for that curved section. And then something else I can try is that fiber striping I was talking about, right? Do I need to add fiber in every single layer? In this case, I probably would, because tube bending dies can be thousands of dollars. So even if we add a little too much carbon fiber, that's okay. But if you're really like, oh, well, I don't think it needs this much, I can always use fiber stripes. And that will allow me to kind of thin out the amount of fiber being applied to that part, right? So I can say the fiber stripe count. I can say how many stripes that I want. So maybe I want, still probably a lot, maybe 20. We're gonna have 4 layers of fiber per stripe. We can apply those changes and you'll notice that we'll now have 20 different sections of fiber. And each of those sections has 4 layers. And you'll see that do that here in a minute. So fiber stripes can be incredibly useful if you want to add more strength, but you just want to add strength generally, if you don't have a very specific location of a force being applied. Awesome. So you can kind of see what these stripes look like. They look like full stripes. I recommend playing around with that a little bit. And then the final location where I want to add that continuous fiber is under the bolt heads, right? So I always like to ask the question, what do washers do? When you're adding a bolt, what do washers provide? Well, washers will help distribute the amount of force from the bolt head onto the part. What if we don't want to use washers? Luckily for us, we have something that will work pretty well. And that's going to be our continuous fiber, right? And so we can use the continuous fiber to help distribute the load of the bolts onto the part itself. And again, very similar concept here. I'm going to head to the 2D view, find where those bolt heads are. And again, you'll see the little squiggles, which indicate there's a solid section there. Find out exactly where that ends. There you go. And I can add fiber there, right? I want to make sure we talk about some applications and get time for Q&A. So I'm not going to go through those bolts. Actually, I think we have some. I'll do it quickly. Okay. So again, create override, add fiber, 3D view, select 4 layers, maybe 4. There we go. Create override, add fiber, right? And it's kind of tedious, and that's because it is. But the more confident that you get with adding fiber, the easier it becomes. And you can probably guesstimate a little bit more when you, again, become more comfortable with this. And then I would do the same thing for the top set of bolts, right? I'd find out where the bolt head would be sitting, add my continuous fiber in my 2D view, go to my 3D view, right? And you see the idea, right? And so again, the biggest things when it comes to reinforcing your parts to be as efficient as possible is to locate the forces, choose your orientation based on where those forces are being applied, right? Because you have to worry about the z-axis being weaker. Based on that orientation, you're going to apply fiber in 2 locations. And that's going to be the very top of the part and the very bottom of the part to increase that stiffness, that sandwich panel. And then where you see the extremes of those forces. Again, I like to keep everything uniform, just to make sure that it doesn't warp or you don't have to worry about that. Okay. So that was just a very quick demo of how to path fiber. Again, if you're a little bit more concerned about this and want to work more with fiber, we will have some upcoming Eiger classes that will help a lot more with that. But I want to go back to some applications. Where can I actually use fiber? Right? A lot of these fibers can be used for overlapping amounts of application. If you have one fiber that you prefer to use, you can probably use that for a lot of your cases. So again, we always want to think about what this part needs to do. What is the success criteria? In this case, right, this part needs to be very, very rigid under some load. Our most stiff fiber is carbon fiber. So any parts that need to be incredibly rigid, you're going to want to add that continuous carbon fiber too. So carbon fiber, right? It's going to be your incredibly high strength tools. If you're putting something in a mill or a lathe to use as a conformal gripping surface to hold a part, you may want to use carbon fiber, right? Because you might have some amount of rotational forces being applied. When you're machining, you don't want your part to move around, so you want something relatively stiff. So anything that needs to be really, really strong and really, really stiff. Something else that might be useful is for like robotic grippers. Depends on what that robotic gripper is doing. You might need the stiffness, or you actually might want to use Kevlar and get a little bit of give to it as well. So in this case, again, what fiber should you use? Answer that question to yourself in your head real quick. In this case, this isn't really being a lot of, like, not a ton of forces are being applied to this part, right? You're really just reaming out a hole. And again, carbon fiber is really expensive. You can just use fiberglass for this. Now, if this was put in a CNC or something a little bit more intense, carbon fiber might be better. But just for reaming a hole, soft jaws for this would be fine in fiberglass, right? So this is going to be maybe potentially your, I don't want to say lower strength tools, because you can just use onyx for that. But this will help if you need a little bit more strength, again, than just plastic, but it won't give you that high strength of the carbon fiber. And these are some gripper draws. Again, you have some options here. In this case, there's a lot of impact loading going on. And whenever we have any impact loading, carbon fiber is going to work great. Another thing about carbon fiber that I forgot to mention is that it fails very gracefully, right? Carbon fiber, when it fails pretty catastrophically. It's gonna it's not gonna explode, but it's gonna be not pleasant. So you have to be a little careful. Kevlar, however, right, it bends, and then finally fails because it's stretched out too far. So if you're worried about any sort of more explosive breakage and you need something that's going to fail gracefully, Kevlar will do that very well. So again, cyclic loading, Kevlar is incredible for that. So end of iron tooling, Kevlar is really great for. Any sort of cradles, right? If you're throwing something really heavy on something really light, Kevlar might be good for that. Again, really going to be impact resistant there. Really good for wear stops and things like that. And then finally, this is just another example. This is a low temperature, kind of low temp plastic molding, or polyurethane probably. And so this part still needs to have some amount of clamping forces, and there's going to be some heat applied to this part as well. And so HSHT is great. If you have any polymer molds, again, low volume prototyping injection molds, and these are, again, lower temperatures. High strength, high temp does increase the heat deflection temperature, but it's still a plastic and it's still liable to melting, right? I can't pour metal in this. And this is one of, again, my favorite tools. This is from the Wartzia case study. And this is a lifting tool. They use carbon fiber for this, right? Because they're lifting a really heavy piston there. And you don't want that dropping on someone. So you got to be really careful with lifting tools. And if you're going to use fiber for a really complex application, you have to test it, right? Right now, there's some like FEA type things, but you really just have to test it to see if it's going to work effectively. And that's totally fine, right? Later this year, right, we acquired a company called Teton, and Teton simulation will allow me to add fiber automatically based on the forces that I input, right? At some point. So eventually the question to where should I add fiber will be a lot easier. But for now, these are the steps that I have to go through to add fiber here. All right, just to kind of wrap everything up here, right? You actually don't need that much fiber in a lot of applications, like the tube bending die and that lifting jig. Those are really high strength applications. I'm using a lot of fiber, and no matter how much fiber I put, it's still cheaper. That's not going to be the case for a lot of your applications. And the steps that I show you will help optimize the amount of fiber that you add. So instead of a part costing a couple $100, it'll cost less than 100. Again, fiber reinforces really only on the X and Y plane. You have to be a little careful with that. Parts can be incredibly strong, right? In the follow-up email that we'll send out, I'll make sure to attach that YouTube video of that chain link. That chain link goes up to like 22 tons, but it's insanely strong. Fiber is great for tooling, fixturing, robotic grippers, anything that you need a little additional strength. Honestly, like you can use Markforged parts for a lot of applications that you probably don't think it'll work for. And that's what my team helps out with, right? Me, and if you've met Michelle, we are on the customer success team. Our goal is to help our customers succeed in their applications. And so after this, again, we will be reaching out to everyone who has attended to answer any follow-up questions and introduce ourselves a little bit better. Again, fiber strong in tension, and then sandwich panels increase the stiffness exponentially. Again, this was a very quick 1 hour, 45-minute session. I cannot get through everything that I want to in this time. So I did the best that I could, but we also have Markforged University. If you're not familiar, Markforged University goes really into depth on a lot of these concepts, right? And then I mentioned before, but we also will have a customer Eiger training. The first one that we have is starting August 25th. This is going to be a basic edition. It's going to focus more on the settings, not so much the fiber itself. There will be more advanced courses later on, but we're just starting off with a basic edition, and we'll go from there. So that link will sign you up for a customer Eiger training if you're interested. Okay, so we got about 13 minutes here. I got some questions. Let's go ahead and take a look at all of those. All right, so first one I got here is, what is the maximum fiber fraction? So that's a great question. And you can have your part be a lot fiber, a lot of fiber. I don't think we have a specific max. The only thing we typically require, and you can adjust this, is 4 roofs, 4 floors, and 2 wall layers of onyx. The rest of it can be fiber. But again, fiber does not fit in every single spot because there is a minimum fiber path length and things like that. So that's something you have to be aware of. Got a question asking if I'd recommend Onyx for vanes inside of vacuum pumps. Onyx does hold a vacuum really well. We have a video, and this is potentially something that I could answer out, or I can send out later, but we have a video of a robotic gripper that pulls a suction to pick up lids. So you can definitely pull a vacuum through Onyx part. It works much better than applying some pressure to a part. All right, got a question here asking, why apply the carbon fiber to the bottom of the beam that is under compression force? Is there a cost value to this method? So that's a great question, right? Because I mentioned before that carbon fiber or any fibers do well in tension. But even when a fiber is in compression, you actually still get that fiber in tension a little bit. It's hard to explain, but let me see if I can draw it out here. 1 second. But long story short, right? A few reasons we do this. First of all, even in compression forces, there's still going to be some tension force, so it still helps. Secondly, it is going to be where those high level of forces is going to be located. And also, again, kind of the third thing that I mentioned is you want things to be uniform because it can lead to distortion and warping if it's not. So honestly, the 4 layers of fiber really isn't that much. So it's only usually like a couple of dollars. So it's usually worth it, in my experience. What happens when a part is loaded repeatedly? I would fear from the plastic layers would delaminate, meaning the fibers are unable to transfer stresses through the matrix and to other fibers. That is a great question, and it depends, right? It depends, and that's really hard for me. We can talk later, but it really depends on what kind of loading conditions you have. We have a ton of tricks that really, really help you create a successful part no matter how you're loading it. But we've had parts survive through like vibration chambers for like thousands and thousands of cycles. So it's not something that we really have an issue with. Now, if you're trying to like pull the part in Z, that's a problem. But there's some ways that we can fix that. And again, I'm sorry to be so vague, but again, either me or Michelle or Zach or Ron on the customer success team will be reaching out to anyone. So if I didn't fully answer your question, because we unfortunately don't have a ton of time, definitely let's talk about that. So question, striping seems to have layered strength. So does striping pattern provides more strength than a sandwich panel pattern? So you typically want to add, yes, long answer or short answer, yes, it does. So striping will provide more strength, right? Because you're adding more fiber. Sandwich panel just adds the bulk stiffness, right? If we think back to the like 1/h³ formula that we saw, that sandwich panel adds the max amount of stiffness to our part, which is why we use a sandwich panel. And if you need much more strength, you can add striping as well. And then if you need more strength than that, then you have more of a solid fill fiber part. So got a question asking if carbon fiber can penetrate the weld line. And I'm assuming you're asking about if carbon fiber can kind of penetrate the walls between the layers when you're printing. It's honestly not something you have to worry about too much. It certainly can. That's why you want to make sure your printer maintenance is up to date, right? If you see carbon fiber or any fiber sticking out of the edge of your part, do the fiber nozzle XY offset. That will help prevent that. And I think that's the biggest thing. Usually it's not too much of an issue because you're still going to get weakness in the Z direction, regardless of whether you have fiber or not. But again, there's ways around that. You can add bolts like we did in that tube bending die example. Any recommendations for improving wear resistance? Again, that's going to be Kevlar. Kevlar is a great tool And so again, if I add Kevlar, I may wear through the onyx surface, and that's okay, right? I can change the wall layer to maybe 1. So it wears through that onyx surface, and now I just have the Kevlar sticking out. That will really increase my wear resistance because Kevlar is much more wear resistant than traditional onyx. Another thing to keep in mind here is that you can always use inserts, right? If you need something to be a little bit smoother of a glide, maybe you want to use a Teflon insert and add that to your part as well, right? Any capability that you need, you can traditionally use as a insert. So I know a few people are asking about the MFU class. So the MFU classes that we have are something that you have to purchase seats to. You can talk to your Markforged sales rep or your Markforged authorized reseller rep, and they will be able to help you get access with that. Also, these recordings, I believe, are being sent out because I know a few people will be asking that. So you can always refer back to this later on if you need to. I got a question asking if we could just review the part when we were talking about the cross-sectional area of bending. Yeah, let's go ahead and just kind of show that one more time here. So this is that section that I was talking about, right? Where you have the force being applied. We look at the cross section, we can see the extremes of those forces are at the very top and the very bottom, right? A very high tensile strength on the top of the part and a very high compressive strength on the very bottom of the part, right? And that's going to be where we add fiber. So someone asked if they could see the slide again, so I wanted to pull it up for them. How does onyx in reinforcement react to prolonged sun exposure? I mean, luckily, reinforcement adds a lot of strength, and that's not going to be really exposed to the sun as much as like the outer onyx shell. It does pretty well in the sun, right? It's not like a photocuttable polymer that's just going to fall apart, but it's still like a nylon based. So that's something you'll have to probably test out. But again, adding continuous fiber really, really keeps everything together and allows it to behave better than just traditional nylon would. I think that's all we have time for. Thank you guys so much for joining me. The questions, I know there's still a few left. I try to get to as many of the ones as I could. I will follow up, and maybe not me, but someone will follow up after this session so that we can kind of chat about your experience and we can talk about any other questions that you may have had. Again, we're going to be doing a similar session to this next month. So I appreciate you guys all for taking time here. And I hope you have a wonderful rest of your day.